Hello, this is Kevin Burke from WFO Chicago, and I just want to give you a rundown on the top-down precipitation type forecasts using the layer energy areas. This is a process that's similar to that of Bourgouin. So first of all, just a little bit more background on the top-down approach. There's, again, three important layers. We need to know first, do we have ice present in our clouds? Are our cloud tops colder than -10? We need to know information about the mean temperatures of any above and below freezing layers in our column. And finally, we need to know the residence time in these layers. And the residence time of our hydrometeor in these layers depends on the depth of the warm and cold layers, as well as the terminal velocity of our hydrometeor. Well, if we go ahead and assume that number 2 here is constant, then this basically breaks down our dependence thermally on the mean temperature of the warm and cold layers, and then of course the depth of those layers. And if we put these together, then we can define an area method, where now our surface hydrometeor type is now of course still dependent on whether or not we have ice presence, but thermodynamically it's now dependent on the areas of these warm and cold layers. Now, the max TW aloft method assumes that the mean temperature or the maximum temperature in the layer is proportional to the depth of that layer. This, however, is not good assumption for deep isothermal layers, as we'll see. So just to talk a little bit about what positive and negative layer energies are, you can think of them as positive or melting energy or freezing energy. So again, this is a method similar to that of Bourgouin, where he measured the areas of the above and below freezing portions of the soundings in terms of energies, a joule per kilogram. This is very similar to that of CAPE. But again, unlike the traditional top-down, the layer energy technique accounts for the depth of the warm and cold layers as well. Alright, so a little bit about the layer energy versus the traditional top-down. Overall, you're still kind of doing the same thing you would with the traditional type. You need to know if there's ice presence in your cloud. But the one thing that is different is, again, the fact that we need to know how much melting and potential refreezing energy we have in our profile. Take these two soundings here, for example. They both have similar maximum temperatures aloft. But as you can see, the depth of these are quite different. So the question would then become, would we expect the same precipitation type at the surface in these two different environments? So in this sense, the maximum temperature aloft does not necessarily tell us the whole story of the melting potential of our hydrometeor. However, if we use an area method that gives us the energy in that layer, this is going to provide us a much better idea of what our forecast precipitation type would be at the surface. To consider the idea of the different energy layers, you can think of these four possibilities. First of all, you have really no layers at all. You're pretty much below freezing throughout the entire column. So assuming you have ice present in your clouds, that would be a snow situation. The other ones we get into, you have basically a surface melting layer. The next one, you had two layers, so now we have a warm layer aloft over the top of a cold layer near the surface. And then you can have 3 or more layers where you have above and below freezing conditions. So the top-down question, will there be enough energy in these layers, warm or cold, to produce phase changes? So as we said in the first example here, that's pretty much a snow event, assuming you have ice present. Otherwise, you're talking more of a freezing drizzle. The next case here is simply a rain or snow question. Our surface temperature is above freezing. The question then becomes, does our hydrometeor or snowflake melt before it hits the ground? The next case here, the 2 layers, we pretty much have the potential for snow, sleet, or freezing rain. And really the answer is going to ultimately depend on the magnitude of these layers. How warm and how deep is our warm layer, and how cold and how deep is our cold layer beneath it. And the same can be said too for the 3-layer technique. Ultimately, The precip type is going to depend on the actual magnitude of these different layers. Okay, to actually determine your precipitation types, we're going to assume that we have ice nucleation present. So of course the first one's pretty easy, no layers, so with ice nucleation we expect to get snow. But then we look at our other layers here. The one layer example where we have the warm layer near the surface, to determine whether or not we're going to get rain or snow, we're going to have to examine our surface-based melting energy, or total melting energy, if you will, throughout the sounding. And that will, in a sense, tell us, do we have enough energy in this particular environment to melt our snow and result in rain at the surface? If not, we're probably going to get some snow mixing in for the surface. The next example here, our warm above cold layer, we're going to have to compare our melting energy aloft to our refreezing energy near the surface. So this is ultimately going to tell us what our precip type might be. If we have warm layer aloft but not a lot of refreeze potential near the surface, we're probably going to be looking at a freezing rain type environment. In contrast, if we have a warm layer aloft above a pretty cold layer, we're probably going to start to favor sleet and possibly snow as well, depending on the strength of this warm layer aloft. And the same can be said too for our multi-layer case here, 3 or more layers. Pretty much it's going to come down to the potential for refreezing, for sleet, and if we have enough melting energy throughout the column to get rid of the snow potential. So overall, the layer energy technique works by determining the total amount of melting and freezing energy in the layers of our sounding. So again, it's the same concept as CAPE. We're talking about energy here that's measured in joules per kilogram. So you can think of the total positive energy as being more representative than the maximum temperature aloft, in the same way that CAPE is more representative than the lifted index in forecasting the potential for summertime convection. So ultimately we can use the energy values here to estimate the probabilities that a falling hydrometeor will melt or refreeze. Overall, the more warm air in a layer, the greater the chance you're going to melt it. The more cold air in the layer beneath it, the greater the chance of refreezing. Alright, so Bourgouin originally did this research here back in 2000, and he looked at 119 rain versus snow cases and 54 freezing rain and ice pellet cases here. And basically what he found is that in environments where you're under about 10 joules per kilogram, you're talking about a mainly snow environment. Get warmer than that, so you're above 10, you start to favor rain overall. But there is some overlap, and the reason for that is there are some unknowns there. Snowflake characteristics, the overall size of the snowflake, and the speed. The terminal velocity is assumed to be constant here, as we said on the first slide, but that isn't necessarily the case. You also have problems with the representativeness of the sounding, possible model errors as well in the forecast. So there still are some unknowns.
Well, the next talk will focus more on the GFE aspects of the modified Bourgouin technique. Just wanted to give you a quick Well, the next talk will focus more on the GFE aspects of the modified Bourgouin technique. Just wanted to give you a quick sneak preview of what we'll be looking at. First of all, there's going to be 2 new grids that we're going to be utilizing. The first one is what's called the positive energy aloft, and this simply is going to represent the total wet bulb melting energy above 2,000 feet AGL. This is basically going to be replacing the maximum wet bulb temperature aloft. Secondly, there is the negative energy in the low levels, and this is going to be representative of the total wet bulb refreezing energy below any warm layers aloft. To actually get negative energy in your negative energy grid, you're literally going to have a situation where there is a sub-freezing layer beneath a warm layer aloft that's above freezing. So this will replace your probability of refreeze sleet. And if your surface temperatures are below freezing, The positive energy aloft grid, which here's a nice example here, is going to help dictate where your snow probabilities will be. The graph up here shows positive energy aloft and the percentage of snow chances. Overall, you can still get some snow chances, some good snow chances with positive energy aloft as high as about 10 to 13.5 joules per kilogram. There'll be some melting, but snow will still be possible. However, once you get more and more positive energy, your probabilities of snow are going to dwindle quite quickly. And once you get about 20 joules per kilogram, which represents the green areas in the figure down here, that's considered too much melting, so snow will not be possible anymore. Now it's important to note that if your surface temperature forecast is above freezing, if you have any positive energy aloft, you're going to get a rain outcome. And this is because of the assumption that you're seeing just the extension of your warm layer at the surface in your positive energy aloft grid. Also in this case, since we're dealing with a simple rain to snow type scenario, there is no warm layer above a sub-freezing layer, so our negative energy is simply zero. If we take a look at our surface temperature in this case, notice that areas across north central Illinois are below freezing. Compare that with the positive energy aloft, which is zero. This is going to be an area where we're going to see snow outcome. Further to the east, you see we start to get some positive energy aloft, granted very small amounts, but our surface temps are above freezing, so we will simply transition our forecast quickly over to rain as we head towards northeastern Illinois. So key takeaways again here with the positive energy aloft grids, not necessarily to memorize exact values, but once we get into the green areas, which represent positive energies in excess of 20 joules per kilogram, it's going to be too much warmth for snow to occur. And if your surface temp is above freezing and you have any positive energy aloft, snow is going to be set to zero and rain will be the primary outcome. If you have no positive energy aloft, but your surface temperatures are in the 35 to 37 realm, you're going to get a rain-snow outcome, and this is similar to the traditional top-down method. So your surface temperatures will be important in these cases where there's no positive energy aloft. It will dictate where your rain and snow outcome will be.
Okay, and then for sleet versus freezing rain environments, Bourgouin found, of course, that sleet requires the presence of a sufficiently cold layer beneath a melting layer aloft. So in this case, Bourgouin found a good relationship between the melting energy aloft and the refreezing energy beneath it in the low levels. So overall, his sleet cases tended to possess more magnitude of refreezing energy near the surface. Likewise, the freezing rain cases tended to possess much less refreezing potential near the surface under the warm layer aloft.
This figure here on the left-hand side is pulled from the original Bourgouin study back in 2000. And he used a really small sample size to determine the function between the positive energy aloft and the negative energy in the low levels to determine environments more favorable for freezing rain versus sleet or ice pellets. Using a much larger data set, over 200 mixed precipitation cases across North America over the last several years, we were able to calculate the same melting and refreezing energies in terms of wet bulb rather than the thermal profile. And in doing so, what we found was for some of these cases where we saw very, very large melting layers aloft, we did not need nearly as much refreezing energy as the original Bourgouin threshold suggested here. This is the original Bourgouin for reference. Instead, we find a much shallower slope to our function between the melting energy aloft and the refreezing energy in the low levels beneath it. So freezing rain events would be favored for refreezing energies generally less than 90 joules per kilogram. As you get more and more cold air near the surface, higher levels of refreezing energy, especially above 100 joules per kilogram, you start to favor at least a mix containing sleet. Looking at some box and whisker plots, which is always fun for these events. Notice on the bottom here I've got the different samples. We had freezing rain, pure sleet cases, freezing rain and sleet, and then a mix of freezing rain, sleet, and snow, and then finally just snow and ice pellets. Notice that there isn't a lot of difference in the amount of positive energy or melting energy, except for the cases that contain snow. Those tended to see less of a warm layer aloft. However, if we look at the refreezing energies, we see a big difference here between cases with just pure freezing rain and those that contain some type of sleet mentioned, as we see here. Notice there's a clear demarcation around 94 joules of negative energy, where if you get lower values than that, you started to favor having sleet contained in the mix versus just that of pure freezing rain. Following our transition zone that we defined on the previous slide from our research, we modified the thresholds for determining sleet versus freezing rain environments using the wet bulb energies. So in this graph here, we've got the positive energy aloft in joules per kilogram, and on the y-axis we've got the negative energy in the low levels. So this represents how we would derive our probabilities of weather types for sleet. So as we get less than 50 to 60 joules per kilogram negative energy, we start to introduce a very slight chance of sleet. You can see, however, as we saw in the box and whisker plots, really our sleet probabilities really start to increase when we get close to 100 joules per kilogram. So once we get into that range and even higher for the refreezing energy, we would call that 100% for our probability of weather type of sleet. And we see decreasing probabilities from that level down to around 50 joules per kilogram. Below that, in this area, you can see we would set it to 0. This would likely be a freezing rain type environment. And sure enough, if we bring the pot liquid or freezing rain, this would depend on our surface temperatures, notice that in the area we set the sleet to 0. That is where our freezing rain would be most prevalent. Notice there is overlap here. We've brought the 100% chances for freezing rain up to a y-intercept here of 105 joules per kilogram. So again, you're going to get mixed zone, so it could be messy during mixed precipitation events. But we rapidly decrease our freezing rain probabilities above this value, with them dropping to a low of 20% once we get above a y-intercept here of 140 for the negative energy. Notice that we dropped off the probabilities quite rapidly here once we get below about 5 joules per kilogram of warm air aloft. This was done to reduce some of the false alarms for freezing rain events for very cool warm layers aloft. The energy here, once you get below 5 joules, might not be enough to result in total melting of the hydrometeor. For this reason, the probabilities of liquid at the surface, whether it be freezing rain or sleet, are going to drop off considerably. In this type of instance, we would either see snow, or if we're cold enough, we would see a snow and sleet environment. The reason we didn't do the same thing for the sleet as we did here for the freezing rain is the fact that only a little melting can induce some sleet potential. So we did not do that same process for the sleet probabilities.
Okay, so the next question then becomes, well, how does the layer energy improve upon the traditional top-down? Well, as we talked about before, the maximum temperature aloft is not always going to tell us the whole story in terms of the melting potential. In this particular case, the traditional top-down method assumes partial melting of the hydrometeor between about 1 and 3 degrees Celsius aloft for the maximum temperature. And this favors precip type of mainly sleet, as you can see on the graph here, especially between about 2 and 3 degrees Celsius. That's pretty much your predominant precipitation type. But this has a couple of shortcomings, as you see listed here. First and foremost, there can be enough energy to completely melt the hydrometeor in some of these cases. And since the droplet is assumed to only be partially melted, the traditional technique does not consider the low-level cold air or refreezing potential beneath it. And this causes some shortcomings in the sense that the traditional method tends to over-forecast sleet when freezing rain is more likely. If we consider this case here, the maximum temperature aloft in this case was 2.6 degrees, so we're well right in the middle of the sleet category. But if we look at the lower level cold air, if we were to do an energy calculation here, we would find that the refreezing energy would be pretty low overall. And the maximum melting potential here would be enough to result in total melting. So in a sense, we would expect to get a result of freezing rain in this case. And sure enough, that is the precipitation type that was occurring during the time of this sounding. So sleet was not the dominant precipitation type in this particular case. Another assumption that was recently added to the traditional method was to make the forecast for primarily just rain when your surface temperature is above freezing and your max TW aloft is at or above 1 degree Celsius. While this does help eliminate the over-forecasting of sleet events, there are times when it will miss a real sleet event, as we see in this case here from New York, where we actually had good refreezing energy here just off the surface. The surface temp was just above freezing, but again a very cold layer just off the surface beneath a warm layer aloft. So this actually turned out to be a pretty good sleet event with 1 to 2 inches of sleet that occurred in spite of the temperature being just above the freezing mark there. So overall, the benefits of the energy method, it offers a fully comprehensive precipitation type forecast since it takes into account the full melting and freezing energy in the column rather than just assuming that the max and the minimum temperatures in those layers will accurately do so. It's able to take advantage of the full vertical model resolution available in GFE, so we can actually see changeovers that the models are showing. If there's dynamic cooling, for instance, we can see that in the model. And in one of the next talks, I will show an example of that. So overall, too, it's going to produce a pretty darn good precip type forecast, even in marginal thermal environments, especially those with deep isothermal layers, where the current traditional method may not do as well. And overall, it's going to take into account those surface cold layers below all warm layers aloft. So overall, this should result in a much better forecast for freezing rain versus sleet environments. And just to add it on here, you can think of the energy method will do everything the traditional top-down method does, but it will also do more because it will do better in those marginal thermal cases that we talked about.
To illustrate some of the benefits in terms of verification of the modified Bourgouin method relative to the traditional top-down, consider this graphic here, which is known as a performance diagram. If you're not familiar with these types of diagrams, they measure basically your probability of detection here on the y-axis and your success ratio on the x-axis. So a perfect forecast would be in the top right-hand corner, where you have both a high probability of detection and a high success ratio, or basically no false alarm. On the other side of things, if you're down in this area, you pretty much have no skill, no PDO, and your false alarm ratio is 100. So we've got the different types of precipitation here in the mix. So we got freezing rain in red, sleet in purple, and then the blue ones represent snow in these mixed precipitation cases. And there's a lot of them on here just for comparison, but overall the things I want to point out here are the fact that if we look at freezing rain following my arrow here, the traditional top-down maximum temperature aloft method versus our modified wet bulb Bourgouin energies. Notice the increase here in the POD with even a higher success ratio than what we see with the traditional method. Likewise, some of the same things can be said about sleet potential, a big increase here in the POD and success ratio for sleet, and even a higher POD here noted for snow events. Overall, much better statistics here relative to the traditional top-down method, and we even see increases with the modified technique here over what we saw with the traditional Bourgouin. Okay, well that's going to end the first talk on the top-down precipitation type forecast using the layer energy technique. So again, my name is Kevin Burke, and I'm with the National Weather Service office in Chicago.